I guess I'm not used to the kind of politeness you have in New Zealand, because in America, the audience is decreased each time. So and not just for 4 or 5 people. But I'll try to make it not so painful. We've been talking about or what we're aiming to talk about is the theory that works the best, that we know the physicists like the best, and that deals with a part of nature, and that's quantum electrodynamics, and deals with photons and electrons. Most of the time we've been talking about photons. What we've discussed is that mainly the main idea of the talk is to give you some idea of the kind of framework of ideas which theoretical physics needs in order to describe results of experiments. And I think by this time you'll agree, after 2 lectures, that they're very weird indeed, and quite peculiar and difficult to believe. But I'll just remind you or review for one more time a little bit about what happens with photons. And as we've said many times, 2 times before, we have a source here, and the photomultiplier, which makes counts of photons. Even if we have only 1 photon at a time, and if we have more than one way that a thing can happen. And the example I've been making several times is that the light the photon we could imagine could be reflected from 2 different surfaces. If there's more than one possible way that something can happen, the whole structure works as this way. In any situation where you have experiments looking at something microscopic, which of course you have in the end to look at something macroscopic that is large, and the photomultiplier amplifies up. When you have a system like that, you can't predict exactly what will happen, but only the chance that the system operates, that you find something happen here. And this probability is always given as the square, or the circle if you wish, of a thing called an amplitude. And this amplitude is a kind of absolute square. It's a special kind of it's the square of the length. And the amplitude is nothing but an arrow drawn on a plane. Now, when something can happen in more than one way, the amplitude that it happens is calculated by adding the amplitude for it happening one way plus the amplitude that it happens the other way. And when you square that, you get the probability. In a problem like this, we have found that the circumstances or the probability for this event might depend upon how far apart you put the plates, and you get reflection from a pair of plates which varies with the thickness in that manner. And so, this, in our particular example, I finally found out that that was 16%, and that was 8%. From each surface, there was 4%. Now, if this were a more ordinary thing, like you would expect, an ordinary type of reasoning instead of this esoteric subject of microscopic physics, you would expect that the chance to arrive here could be analyzed by saying, of all of the ones that come down, some bounce from here with a certain probability, and some bounce from here with a certain probability. Let's say 1/5 bounce here, or what do we say, 1/25. And 1/25 here would be 2/25 of them. What we would do would be to add the probabilities. We find out that instead of adding probabilities in such logical circumstances, we add amplitudes. In other words, we can sit around and talk about it this way. You say, well, there's a certain, it can go either this way or it can go that way, and we just add the amplitude before we square. But that means that the logic that we can say that it really goes either this way or that way is false. You can't really say that in the common language way, or you're meant to add the probabilities. Because if you were to say it can either go this way, some of them come this way, and some of them come that way, you're at a total loss to understand why, when the thickness is just right, none of them come at all. Because if some of them come one way and some of them come in the other way, the fact that they can go both ways surely isn't going to make it that they don't come at all. But that's exactly what does happen. And so the idea to be able to say that it comes either one way or another it requires that you know what you're talking about. You're not talking about ordinary either one or the other, but either one or the other in the sense of adding amplitude. So it's a crazy game. I still find myself saying, well, it comes either one way or the other. But it is not really true that for a given particle which arrives here, you can say that it either came this way or that way. You won't get the sensible physical idea out of that. As a matter of fact, it's entertaining. The following thing is very interesting. It is possible to put some kind of atoms on the surface here, such that when light bounces off it, they leave some trace that the atom is left in some other state than it was before. So that if it bounced the light from the surface, an atom on that surface would be left in a different state. Likewise, we can put atoms of this kind. It's rather technically difficult with light, but you can do it in many, many analogous experiments in similar situations. Well, imagine we can do that with this. And then we could say, let us bounce the light, and then afterwards look at the atoms and see which ones are excited. And what you discover is, if you have enough here, that you don't miss them. But you forget the cases where you miss. That it's either excited here or it is excited there, yes. In other words, it does look like the photon either goes this way or that way. And when you have the atoms here and you count just those cases in which you can find, you see, I'm worried about the cases where you miss them. Forget the cases that you miss them. And take only the cases where either one or the other atom is excited on one or the other sheet, and ask for the probability of arriving here. And you know what you get as a result of as a function of thickness? A completely different result. If you have atoms there that can leave a trail as to whether light was there or not, you get 8% reflection no matter what thickness. In other words, it tricks you. You're only going to be clever. You know that if you have no way to tell from which one it comes, if the light after it bounces off leaves everything the way it was before, then you get this funny interference effect. If, however, you put something here to see if the light bounced here or here, you can tell it bounced one or the other. It tells you, it leaves the atoms excited. But lo, there's no more interference effect. Why? How do we describe that? It's not hard. It's that we changed the problem. The first problem was, given a source here and material here, what is the probability that for the following event, that the photomultiplier goes off and that the system is left exactly as it was before, that nothing is changed in the glass? That's that curve, the first one. But in the second experiment, we're asking for a different final problem. We're asking a different problem. The problem is, what is the chance, if we have a source here and these layers here, that the photomultiplier goes off and one of these atoms on this layer here, say, is excited? That's a different problem, has a different amplitude. And that has nothing to do with what happens down here. And that amplitude is 4%, or 0.2 rather. Squared is 4%. It has some darn angle, I don't understand angle. Squared is 4%, and the probability that it's reflected from the front surface as detected by an atom there is 4%. Likewise, if you ask for the following situation, that the photomultiplier should go off and the bottom one should have an atom excited, you get also 4%. So you see, if we try to test whether or not it's going one way or the other, then the results of the experiment have changed, or another way, we have to ask about a different experiment. The case of interference is this, that it is such a situation that the rest of the system, the glass, is exactly the same before and after, and there's no way to tell where the light bounced. Otherwise, if you had some way to tell, you'd ask for a different physical result, have a different amplitude and different results. Which means these things I point out because as you've gone along, you've probably struggled to find some kind of a simple-minded explanation of these things. But when you see how annoyingly complicated it gets, I mean not complicated, but curious it gets harder and harder to make a simple model. So we've given up on that. I also emphasized last time that you can get some that one of the things I wanted to emphasize is that things that are very common and observed all the time and which are perfectly obvious are quite different in this world. It turns out that what we thought was obvious is quite wrong and it's much more complicated. Or not more complicated, but just different. In fact, it's sometimes simpler and more beautiful. A particular example we had was that light was reflected by a mirror at equal angles, or that light went in a straight line, and we demonstrated that mysteriously enough,
was the consequence of light going every which way, and not necessarily in a straight line. In particular, I pointed out that if we had a mirror which was made of little pieces of the right spacing and had light coming down this way, it's reflected back that way sometimes, but it has a good probability to be reflected at a special angle. That's crazy. That depends on the spacing here. I have been using light, and we've been using red and blue light. When we change the color of the light, this distance changes, but I have explained in the first lecture that the range of conditions is enormous, and that we can have distances corresponding to hundreds of meters for radio waves, and distances corresponding to spacing between atoms, or even much smaller for other rays. In fact, if these little spots were, instead of mirror pieces, just atoms, which are much closer together, very close together, then it's possible to find photons of such short wavelengths, much smaller than light. This distance is about 10,000 atoms, the thickness there, but here one atom. And when you have light of the wavelength of one atom, it's called X-rays. And when you shine X-rays on a crystal, which is where all the atoms organize this nice pattern, say a crystal of nickel or some other metal, you'll find X-rays coming off at special angles. That was discovered in 1914 and was the proof, they said, that X-rays were waves, but at the time all the other evidence indicated X-rays were particles, and we now know, you all know about this puzzle. At the same time, this was very exciting because it not only determined the wavelength, so to speak, for X-rays, it showed they were the same as light, but much smaller wavelengths, but also that is much quicker variation in time of the amplitude. The amplitude changes slowly with red, faster with blue, super fast with X-rays, super fast with gamma rays, and so on. And not only did that, but by the way, incidentally, by measuring these angles, you could determine the spacing and arrangement of the atoms in crystals, and that's how we've gotten to understand how the atoms are packed in various kinds of substances and so on, which is exciting and interesting all by itself. But I'm wasting time because the lecture's on electrons, and I've been talking about photons. But what I wanted to emphasize was the structure. The structure is amplitudes. We get to talk about them all the time. Only later at the end we square them to find probabilities. Amplitudes add when you have different possibilities. We also taught that amplitudes will multiply when the things happen in succession. In fact, amplitudes multiply just like probabilities multiply, and under the same circumstances. If you had, if we would like, we could analyze this another way. We can say there's a certain, if this were really a chance thing, we say there's a chance it gets from here to here, and a chance it bounces off, and a chance it gets from here to here. It turns out that that's right. You can analyze the amplitudes the same way. There's an amplitude to go from here to here, an amplitude to be reflected, and an amplitude to go from there to there, and you multiply them all together, just like you multiply probabilities. Multiplying, I explained last time, multiplying two arrows is done in the following magical way. You have two arrows, and you make a new arrow whose length is the product of the lengths of these two, and whose angle from horizontal is the sum of these two angles. So in this case, the product, I don't know what the unit, let's say the unit is this big. The product is a small arrow at an angle something like this, which is the sum of the two. Anyway, we find we can add and multiply arrows. The mathematicians call them amplitudes, and mathematicians call them complex numbers, and that's the structure of the world. Electrons were discovered in about 1895 or so as particles, and they were studied and believed to be particles. They behave very much like particles. You could count them. You could put one of them on an oil drop and measure the electrical charge. Electrons responded to the presence of other electrons. If you had a metal plate here and a metal plate here and had an excess of electrons here and a defect so that what's left over is protons here, then an electron sailing through between the plates would be repelled from the other electrons and attracted to the protons and move in a curve something like this. Millions of electrons moving through a wire represent an electric current, and so on, and so on. And the entire picture of electrons as particles going around in matter explained many phenomena, and everything was going along all right. There was some puzzles about how they behaved in an atom. If you've heard about the atom as being a little solar system with a nucleus in the center like the sun and the planets going around like electrons, then you're back in 1900 and something, 1910 or so, because it's quantum mechanical, as it turned out. By 1923, de Broglie suggested that this business about mixture, this wave and particle properties like light, was probably also true of electrons. And though historically, the wave aspect, aside from Newton's era, the wave aspect of light was most obvious, and the particle aspect was discovered afterwards. In the case of electrons, the particle aspect was most obvious, and the wave aspect was discovered afterwards. By almost in 1924, only a short time after de Broglie's suggestion, Davison and Germer were doing some experiments bouncing electrons off of nickel, expecting them to bounce back this way, which they did. But they also discovered that some of the electrons went off on a crazy angle. And when they read de Broglie's paper, I can't pronounce it. Sometimes they call it de Broglie, and sometimes de Broglie, and sometimes de Broglie. It's a French name, so it's hopeless. And they found that these electrons came off at an angle, and that they calculated the angle, what the wavelength had to be, because you know the spacing of that from the experiments with X-rays. They found out that that was exactly right, according to de Broglie's theory, and that electrons, in fact, did the same thing as light in the same kind of dual hocus pocus. In translating the words dual hocus pocus into better English or better physics, it's this: that even an experiment involving electrons going from one source, say a tungsten filament, to a counter of some kind, is exactly analogous to the situation with light. In fact, all of physics, as it turns out, as far as we can tell, is all the same framework. There's a probability for an event, and the probability is the square of an amplitude. And there's an amplitude that an electron goes from place to place. The amplitudes can be compounded by addition when there's more than one way to happen, and by multiplication when you can think of things happening in succession. That means that all the possible events in the world might be analyzable into separate, simple events of which everything is a compound. For instance, is it possible to describe like everything that happens as a series of events? For instance, it jumps, it goes from here to here, it bounces off, it goes from here to here, and so on. I'll give a specific instance in a minute. What does turn out to be true, and this is what the content of the present lecture, is I want to start all over again and tell you, now that I've introduced and I've convinced you about the framework of probability amplitudes, I must give you the laws for the probability amplitudes, and that way give you the complete theory of quantum electrodynamics. It turns out there are only 3 laws, okay? But they have to do with the idea an amplitude that an photon goes from place to place, an amplitude that an electron goes from place to place, and an amplitude that an electron emits a photon. I'll describe them in detail now. Now I would like to give a more complete description of the way the laws of physics look, at least in this partial realm involving only electrons and photons. In order to give this description, I have to include something which I didn't include before, for simplicity. I include now the time. In the experiment which, here it is. In the experiment which I thought I had just erased but didn't, we can ask another question. We can ask, if the source is made to emit a photon at a given moment, what is the probability that the counter receives a count or goes off at a given moment? This adds the idea of time to the things that we've been doing before. We can ask a question that's, in other words, more complete, not only where the thing is and at what time it arrives. And so we have the following world. We have an amplitude inside of space-time, space and time. Things move around in space, and they take time to do so. They don't really move. They have amplitudes for doing their thing, okay? But their thing is done in space and time. You can ask for the amplitude that a photon arrives here at a certain time and an electron is somewhere else at another time, and so forth. Now, in order to describe both the space and the time pictures, I'm going to make a kind of graph which which is very handy. If I call it by its name, you'll be frightened. So I'm not going to call it by its name. I plot the position in space sideways here and the time this way. And I'm going to explain what such a diagram is by taking the old-fashioned world first, not the quantum world, and see what happens. So we take a baseball. It's standing still here. What does it look like on this picture? The space is supposed to be represented this way. Of course, we know space has more dimensions, but I don't have to draw them. I draw one out this way for the other dimension space, and a third one at right angles to both of these and this for the third direction of space. Now, if I represent the baseball by a little plot here, at a given moment, there's the baseball. Later on, the baseball is in the same place. So later on means go along this way. Then later on, the baseball is here. That's the width of the baseball, okay? And later on, the baseball here and so forth. Why did I bother to make it a wide baseball? I don't know. And so here, I could have made it a point baseball and made it easier to draw. The baseball, as a function of time on this diagram, will be represented by that band, all right? Now, if a baseball is moving, okay, it's drifting across the room, what does it look like? This time, I'm going to make a very much smaller baseball, okay? Or you're so far away you can't see the sizing. Let's say it's here now. Later on, it's in another place here, and later on, it's another place here, another place here. So in this world, it'll go so. If it's coasting at a uniform speed, it'll be a straight line. If the baseball goes for a while, hits something and comes back, then it'll go something like this. There was something standing here, right? And it bounces back. Let's say this was a bricks, which were standing still. And that would be a picture of a ball hitting a wall. It goes boink, boink. And I stretch that out this way. Another way to, well, that's, I think, a pretty clear picture. And this we represent situations in space-time. So if I were to, in space and time, which I've inadvertently called space-time, which is what everybody calls it. Now, we could say, for instance, that at this particular place, we had a source which emitted a photon at a certain time. This is the time, and this is the place. Then later we can ask if, at this place, a detector at that time would discover a photon. Now, if photons were baseballs, we could say, well, maybe the photon went straight along here, or what have you. But we don't have to say we don't know anything about how it goes, but you know what the answer is going to be. There's going to be an amplitude, that a photon let out of here arrives here. And that amplitude will depend upon the time of this one and the position, and the time of this one and the position. And I'll call this point for just a moment number 1 point, and this a number 2 point. And then we have a thing which is called the amplitude for a photon to go from, well, to 2 from 1. And that's one of the great fundamental laws of nature, what that formula is for that. It's a little mathematical formula, and it's very simple. I do not want to bother you with exact mathematical expressions because it won't mean anything. It's easy to describe for those who are more sophisticated. Of course, you realize immediately that this formula for this is going to depend only on the difference of the time and on how far you had to move, the difference of the distances. So it's not so complicated. If the difference of the time is t and the difference of the distances is x, then the answer for this thing is this function, but I don't want to bother you with the mathematical thing. Only know that I can write it down in 1 second, and people who know this magic, this mysterious language, know what that means. So that this formula is extremely simple. It's as elementary as it can be. Oh, it really is as elementary as it can be, as it turns out. If we added a couple of principles, then you can deduce what it has to be, knowing nothing except those principles. The principles are as follows. There's a knowledge of the relation of space and time. The way things depend on time and the way things depend on space are interconnected by a law which is the principle of relativity. And that tells us a great deal, limits the functions a great deal. The second proposition is that the probabilities that you get from this must have the property that if you add up the probability of every possible event, you get 100%. And if you make a wrong formula here, it doesn't check. You know, the probability of everything all added together has to be every possibility, which is 100%. Something's got to happen, in other words. And if you get the wrong formula, it doesn't come out right. You find out that the probability of something happens is 1.5, or -2, or something. So adding relativity and that principle determines this almost completely. Not quite completely. I'll tell you a little more about it in a minute. This function, this depends on these two things. Just for the sake of this discussion, I'll call it D, say. Why D? P, for photon. P is for photon. Between 2 and 1. It's an amplitude of a certain size that depends on the distance between the two. You might at first be surprised because when we were dealing with photons over there, we said that the amplitude was rotating and depended on the time by going around proportional to the time, depending on the color of the photon. Nothing has been said about the color of the photon over there. Something's wrong. No, it turns out as follows. I will explain it better later. The color of a photon is a result of the source. The source emitting has an amplitude to emit the photon, which is a function of time, which is going around. When an amplitude for an event changes with time by simply rotating, not changing its length, but by changing its angle, it corresponds in the real world, I mean the world you're used to, the ordinary world, to be a situation in which the energy of the system is definite. And what we've been talking about before were situations in which the color of the photon, the energy of the photon, was definite. And in those situations, the amplitude is turning around in time. This is, in fact, a result of the source. When we go back to discuss things as a function of time, and all photons are exactly the same, there's only one kind. If the amplitude varies slowly, it appears to his eyes a red photon. If the amplitude varies very rapidly, it's an X-ray. It's all the same. It's just one thing. There's only one kind of a photon when you cut the time. So you see, when you discuss it in time also. So you see that things are getting simpler. To represent that a photon has gone from 1 to 2, we represent that by a wiggly line for no good reason. To represent a photon going from 1 to 2. Now the next thing we have to do, that's the first law of physics. The second law of physics, that's all about optics. That's the entire theory of light. It really is. The part that's not in it is how the light interacts with matter, and I'm coming to that. Next law, that has to do with electrons. Oh, I did cheat a little bit, yes, wait. I told you about polarization of photons, which I've left out here. It also turns out that electron has 2 states of polarization too, which is sometimes called spin states. And again, I'm going to leave them out because they don't add anything to the ideas. They just add a little complication to the formulas, which you're not going to work with right now anyway. So if you want them, I'll tell you the exact laws, but this is very close. With electrons, we have a similar situation. I just draw the same diagram because I used up my paper and I rolled it away. But if this was time and this was space, we can ask the following thing. If the electron is known to be started here at a position in time which I call 1, it has a certain amplitude to arrive at another position in time, 2. It then will go from 1 to 2, which I'll draw with a straight line to distinguish it from the photon case. And we need a formula for the amplitude for an electron to go to 2 from 1. And that's a different function of the 2. That is a number that depends on the 2. And I'm going to write it down here. No, it turns out a little harder to write that one. It turns out that that one involves not only the time and the x, but also another number in the formula. It's more complicated than this. And that other number is a characteristic of the electron. It's called its mass. And I'll tell you in a moment a little more about it. In other words, what it this thing really depends on the position 2, the position 1, and the number m, e, the mass of an electron at rest. Mass of an electron. If you put the right number in for that, then that's this thing for electron. If you put 0 in for that, that's a photon. That's this one. That's D. And as we'll see, for every known particle that we hope in the end, for every point-like particle that behaves like a point, it's got to be this way with some m. You can deduce that alone, this formula for this thing, from relativity and this business about the probability of getting to 1. The only possible function is a particular one here, which I haven't written down, but I write it symbolically. It's an arrow, which is the amplitude, a complex number, which depends upon the two positions, and on some number. In the case of an electron, that's a particular numerical value. Now, it would be nice for me to finish the job and write down the formula for that thing, but I can't make it understandable to you, because unless you have enough mathematical background to appreciate Bessel functions. So, but I will tell you a little bit about the function. A special example. A special example, in fact, of the use of such a thing. Suppose that we have a situation where we know at the present moment, time is this way as usual, and space is that way. We know at the given instant that the electron is equal amplitude, exactly the same amplitude, to be everywhere in space. Then the question is, with what amplitude will I find it at this particular place later? Answer. It might have been here, and then it would go to there. Or it might have been here, and then it would go to there. Or it might have been here, and then so on and so on. So what you do is you take for each one of these places, for these 2 points, the value of this E, and then for these 2 points, the value of E, and you add them all together, because those are all alternatives. It might be here, and so on. I could write it this way. The amplitude to arrive at point 2 from places 1, which are all different values of x at a particular time t1, we'll call this t1. This is mathematically complicated and frightening, but all I'm saying here is exactly, perhaps I better not say it this way. What you do is you take the amplitude to go from every one of these points to here and calculate it. Add it together. In other words, you add this thing for a given time, but all different places. And then the answer is very simple. The answer is simply an amplitude of a certain unit length, whose phase, whose angle here, goes around depending on how much time it's been from here to here. Sounds familiar, but it's not a photon. And the rate at which it goes around is very high. It's something like 1 point some odd times 10 to the 20th. That's 130 million oscillations a second. All right? But that time, the speed at which this is going around, if you change this time, is characteristic of the electron and measures its mass. Furthermore, it's pretty obvious that the amplitude to arrive at any other point is exactly the same, because it had all the same amplitudes back here, and if I started with another point here and drew all those arrows and everything, would be the same picture. So the amplitude to arrive everywhere is again the same, but has a different angle. So if the amplitude to be everywhere in space is exactly constant, the amplitude to be everywhere in space stays constant, but changes its angle only. And the rate depends on the mass. A particle whose amplitude is the same to be everywhere in space, it corresponds to a particle at rest, stationary, in the normal parlance. Also, I told you, when an amplitude is such that all it doesn't change anything except in time by changing the angle, it's a state of constant and fixed energy. An electron at rest has a definite energy, which is called its mc square, I think. It's mass times the speed of light. I've taken the speed of light to be 1 in the units I'm using, so that this just goes around depending on the mass. If I had had a heavier particle, the situation would be the same. I'd put a different number in here, but it'd just be that this amplitude would rotate faster in that case. Anyway, there's a simple example of one of the properties of this function, which is very, very simple. As a matter of fact, if you're clever enough, you can deduce from this, plus the principle of relativity, what that function was, but you're not that clever, so we'll let it go. But I'm just trying to emphasize that the particular function, although I haven't written it down exactly, is as simple almost as it can be. Finally, there's one more rule, and that is that if an electron comes to a point at the same with a photon, they come together at a point, an electron and a photon, that an electron can go off from there. It's possible to have a junction. And there's an amplitude that there's a junction. The amplitude that a photon is absorbed by the electron, let's say. Or whatever kind of a junction you've got. We can talk about what the junctions mean. But every time you see a junction, you get an amplitude. That amplitude is given by a formula. C is equal to 0.08542, and so on. A number, just a number. 1. Physicists like to remember this number in the form 1 over c squared. And they write c squared is 137.03599 plus or minus 3, and that's the result of an experiment. That's a magical number, a mysterious number. Good theoretical physicists put that at the top of their bed at night and dream if they can figure out why that's the right number. The fact that we have no idea where that number comes from, and it's one of the mysteries and incompletenesses of the theory, because it would be nice to get that number out of something. It's done by experiment. I'll discuss that problem in much more detail in the next lecture when I talk about the limitations or the incompletenesses of the theory, and also other particles in nature and all the other problems of physics more complete, not just electrodynamics. Well, now let's see. We have just these parts, and I would like to discuss calculating the amplitude for a number of different events so that you can see what's involved. So the first example will be this. Suppose that I have 2 electrons, again, time this way, space this way, and so on. I have an electron, I know its state at position 1, and time, the position time 1, Mach 1 here, and another one at 2. And I would like to know whether at a later time I will find one electron here, well, let's not put it in the same place, and another electron, say, there. All right? So one electron should be at 3, and the other at 4. Now, to find out how to do it, the first thing I do is I suppose that the electron number 1 went to 3, and the electron number 2 went to 4. So I draw a picture like that, and I read the picture mathematically as follows, that amplitude for this event is the product, as we talked, because these are 2 independent things. There's one factor, which is the amplitude that this gets from here to here, which is just that E thing, which is some arrow. And there's an amplitude to get from here to here. If I were writing it mathematically, I'd write E31 times E42. But what I would mean is, I get from the formula the size of the arrow here, and then I'd multiply it by the size for this arrow, and that would be the answer. But that's not the complete and exact answer, because there's another possibility. So I must consider other possibilities that can occur. Another possibility is that it was this electron that went to there. I'm just drawing the same picture over again, but making a recombination. This is 1, this is 2, this is 3 and 4, and the amplitude for this one would be E3 from 2, E4 from 1. And from what you've learned last time about photons, if it can happen in 2 different ways, you add the amplitude. But for electrons, there's a different rule. When it can happen in 2 different ways for electrons, you subtract the amplitude. This subtraction has a very profound and remarkable influence on the behavior of electrons, and is the reason why electrons behave more like particles experimentally than like waves when they were first found. I'll come back to that in a little while. Let's forget this for a while and let's talk about just situations like this that somehow you know it's the same electron going here. This subtraction is extremely interesting. But I'm going to come back to that because I want to concentrate on something else. Well, there's another way that the first thing can happen beside that exchange business, and that's this. It could be, here's the particle at 1, and here's the particle at 2, and the particle that goes to 3, and the other one's going to go to 4. Now, I had them going directly. That was the first thing. But you must add an amplitude for every possibility, so we have to keep on going and adding something. It could be this. Number 1 could go to some place in time and space, which I'll call position time 5. The electron can go to here. Yeah. And then go from 5 to 3 and make a junction here by emitting a photon. And the other one go to the other point where the other end of the photon is 6 and go to 4. Now, if you're brave enough, I'm going to write the amplitude for this thing in a high-class mathematical fashion, and you'll be able to follow it. The answer to this amplitude for this contribution here is the following. E35, E51 times E46 times E462 times, anybody got another guess? What else is in it? D56. That's the P, photon, 5 to 6. And forgot something, C times C. How's it work? If I haven't made a mistake here, there's the amplitude of the electron goes from 1 to 5. And then an amplitude, the electron goes from 5 to 3. Times an amplitude, that's a junction. That's a C. Likewise here. In addition, there must be some amplitude that the photon that's been liberated at this junction has gone from 5 to 6. You put that in too. You multiply all these together by those rules. I know it's getting complicated. We're piling a lot of stuff together. But it's like playing checkers. There's a few rules, and you just have to use them a lot. You got triple jumps, but they're nothing but single jumps repeated. So it's like each of the thing is simple. It's just repeated and repeated. So we calculate this thing and add it, that amplitude with all its arrows, and multiply to that one up there. Let's forget the other case for a minute. Add it to that and be improved accuracy. It's not quite finished yet. Why? Because, of course, you could have something like this. And so on. I mean, there's all kinds of wonderful things. We'll come to all kinds of wonderful things in a minute. You got 2 of them going across and so on. Well, this is a hopeless task. And you got to keep adding and adding and adding and never get finished. But we're going to get a good luck. Good luck. You see, this amplitude has a number of factors in it, but it also has C times C. And C times C is a relatively small number of the order of 1%. And as it turns out, the contributions from a picture like this under ordinary circumstances is about 1% of the contribution of this. The reason I say that under ordinary circumstances, it can happen that you've got a situation where this one is adding a lot of cases and a particular picture cancels out by interference, and then something that's 1% smaller is the whole thing, and so on. Forgetting all about that, each time you add an extra photon, you add a C square, it makes it 1%. So therefore, if I make a picture like that, it's 1% of this one, which is 1% of that one. So by the time I got down to this one, I got things correct to 1 in 10,000. And if I would get to the I got to putting 3 of these darn things across, well, then I got to 1 part in a million, and that's why we can calculate so accurately, because we can do 1, 2, 3. Never can get to 4. It's too complicated. And there's another thing I forgot to say, and that is that where's 5 and where's 6, you're sitting there asking. Anywhere. Yes, anywhere. Those are all possibilities, and those are alternatives. 5 might be here and 6 here, and you have to take that, then you have to put them somewhere else and add them and add it and add it for all different places that 5 and 6 can be. All right? So what I mean to do is to add this together. for all places that 5 can be and all places that 6 can be. I mean by its places, positions in space and in time. If 6 is later than 5, you're inclined to say the photon went from 5 to 6. If 5 is later than 6, that is, if I got this around that way, you would say the photon went from 6 to 5. In other words, in one case, this emitted a photon which the other one absorbed, or vice versa, this can emit a photon that absorbs. But it's a funny thing in relativity, it's very difficult to say when two things are nearly at the same time, which is ahead. And this whole business of trying to decide when they're nearly at the same time, which one is emitting the photon and which one is absorbing the photon is an irrelevancy. This function for photons is large when the distance is big, only when these two are at such an angle that you usually can get there at the speed of light. You usually think light goes at the speed of light. You used to think light went in a straight line. Light goes on many different lines, and the result is it looks like a straight line to a gross sense. Light goes at different possible speeds, at different kinds of angles here, and the superposition when the distances are big is that it gives only a result when the speed is at the speed c. So I have now finished telling you, well, one thing I cheated a little bit in the fact that I left out the polarization. And this junction thing has a whole lot of different numbers, depending upon different polarization cases. It could be one kind, another kind, another kind, different combinations of polarization cases here. And those numbers are those are a little 1, aside from this factor. It's either a 1 or a -1, or sometimes a pure vertical thing like that, or sometimes a pure thing like that. Very, very, very simple. So if I'm going to leave out polarization altogether, I'm not giving you a wrong impression that the junction is just C, this number, times 1. It's not exactly 1. Sometimes it's -1. It's a little different, but that's for different polarization cases. But I don't want to deal with that any further. From that, all the phenomena of nature occur, result. For instance, you know that the light can be scattered. It comes from the sun and is scattered by atoms in the sky, so you see blue sky. How does it work? If we have an electron, well, excuse me, let me go in a slightly different order. I'm going to come back to that case. I stepped on my own cord that time and it choked me. I have now recovered enough to continue. In order to understand the behavior of electrons in atoms, we have to add one other feature, and that is the nucleus. The nucleus is not completely understood, and I will not give you the correct laws for the behavior of nuclei if I could. I wouldn't waste any more time lecturing here, but I would publish it immediately as it is unknown. These functions that we know so well must be the right functions when things behave like points and have no internal structure. And it has turned out experimentally that the electron and the photon have no internal structure to as small as we've been able to look so far experimentally, and that is to distances which is 10 to the minus 15 centimeters, approximately 10 million, 1/10,000,000th of the size of an atom. Small enough. So it looks like a point. But the nucleus doesn't look like a point. But for many, many experiment phenomena in atoms, you can approximate by supposing the nucleus is a point. And insofar as you can approximate the nucleus as a point, you can do the same trick with a nucleus, but put the mass of the nucleus there. That is only approximate. For the electron, this is right. For the nucleus, it's approximate. So if I want to describe a hydrogen atom, I have to represent the nucleus, so I'm going to represent nuclei by lines, thicker lines, double lines, like this. This is an electron, that's a photon, and this is a nucleus. A nucleus, let's say to take a hydrogen atom, the nucleus is just a plain proton. And it looks fat because we don't understand it inside, But the electron is nice and thin, and it goes along, and nucleus might emit a photon which interacts with the electron. It could be that over a million years, or a few millionths of a second in the practice, that you can emit several times photons back and forth, and the electron in general does some sort of a dance like so around the proton. Calculate the total amplitude, an electron and a proton down here. Still looks like an electron and a proton after a long time. You have to add the possibility that the electron and proton just went directly with ease, or that the electron went for a while and there was an exchange and another one of photons. Both of these things happen, and the interference between them has an effect on the motion of the electron. In the presence of a proton, an electron does not move the same way as it does when it's in empty space or free of a proton. When it's free of a proton, the amplitude to find an electron at a certain point is given by this function. As a matter of fact, you can show, in a manner similar to the case of light, that if there's nothing but an electron in the space, it appears to go at a uniform speed in a straight line. That is through the interference, of course. The same way with light. But when there's a proton in the neighborhood, or any other source of photons, but let's take the case of a proton. As the electron is moving, its amplitude keeps changing because the amplitude of the situation keeps changing because of the exchange of the photons. And the result of that is that the amplitude to find an electron anywhere is altered by the possibility of exchange of photons with the proton. And that is all computable and quite complicated. That's the theory of atoms. But if we have a very large-scale event in which things are far apart, and I drew it somewhere, but it's long lost. If I had some metal plates with an excess of protons here and some extra electrons sitting here, then an electron going along here, and mind you, this is on a very large scale compared to my other drawings where atoms were big there. Now they're tiny. There could be a photon go across here, another photon, another photon. These billions of photons going across are all very long wavelengths, a few centimeters, half a centimeter, contain very low energy and hardly disturb the system. The thing that's emitting them can emit them without any change. It's such a small energy. At any rate, the main point is that the electron in going along in this space here is not going along the same way as it would if there were no plates. And when you calculate the chance of finding an electron to go from here to here, you'll discover also, just like we did with light, that in this approximation of large scale, the only path which is important is a special curved path, not straight, because the photons are altering the amplitude. Actually, yes, that's right. The interference, I got the curvature in the right direction. That's what was worrying me. In the case of light, you remember that there was an angle at which the amplitudes came in, and if we added all these amplitudes together at slightly different angles, the only path that was important was one in which the angles are not changing. In the case of light, the angle depended only on the time. And so it was time should be not changing, or least. In this particular case, the quantity, which is not changing, is more complicated than the time. It's a more complicated thing. It happens to have a different name. It's called the action. And the pairs of particles can be calculated by computing a certain quantity on a path called the action. And the path takes the path, the curve, which looks like the curve of least action. This way of putting the laws of mechanics was discovered many, many years ago as what we call classical mechanics. The relationship of quantum mechanics, quantum mechanics is exactly right, and the classical mechanics is an approximation. The behavior of light jumping all around as before is right, but the idea that it goes in a straight line is an approximation. The idea that an electron goes in a curve is an approximation. It's really amplitude jumping about. This example, however, shows something interesting. In many circumstances, it's true that we have long wavelength photons which can be emitted because they contain so much little energy without disturbing the source. And whether or not they're absorbed by an electron is a matter that doesn't make much difference to the energy of the electron. And so we can find an electron moving in a region in which there are available many photons, enormous numbers. The wavelengths are so long, the energy is so low, the numbers are very large. But they're all about the same. Then we can describe this electron by saying it goes in a straight line except it's disturbed. It's disturbed by the possible presence of photons. We say, in an old-fashioned language, that there's a field in the neighborhood, an electric and magnetic field, which alters the motion of the electrons. But what this electric and magnetic field is amplitudes to find photons in very large numbers, under circumstances where their energy is so low that it's easy to emit them. And that's the earliest ideas then about the motion of electrons was that they were particles being bent by forces generated by fields. This is now all passé. Instead of that, it's just the exchange of electrons, exchange of photons between the electrons or between a nucleus and the electron, the amplitudes for which are all given by this little constant, and the amplitude for the photon to move is given by a known function, and the electron likewise. And that's all there is to it, and from it all the rest of the laws of physics come out. Another example is the scattering of light. Light, according to that view, would always go in a vacuum in a straight line, or however it goes in a vacuum. And if the distances are big, it would look like a straight line. But we know that we've talked many times about light being bounced and reflected from the surface, or light going slower in materials and so on. I have to explain that. What's involved there is that in matter there are electrons, and if this is a typical electron moving along, again, time is this way, unlike this diagram. This is an ordinary diagram moving through a piece of material. We're moving through some place. But here's time again in space. We can have a photon coming in from the outside, hitting an electron in an atom, say, or anywhere. And after that, a photon is emitted by the system. So a photon comes in and a photon goes out, and it's even possible that the electron's condition that was before is restored again, although temporarily it's been changed. Of course, if you like this game, you can imagine another diagram. Let's see. Another possibility. Crazy idea, isn't it? That it's emitted before it's absorbed. Yes, you add that too, both together, and it comes out right. Don't worry about anything. You just add everything. It's only the sum of these two which is the right answer for the scattering of light. So you see that when we have electrons present, a photon can come in and come out in some other direction. That is the basis of the rules that we made before. And I should, for completeness, repeat these rules and explain them all over again, because in this system I had a different rule. I talked about photons having an angle dependent on time, and everything was kind of funny, and it doesn't look like it here. So I have to explain that just a little bit. It works more detailed. Now, this is a more detailed description of what happens in here. First, we were supposing that we had monochromatic light, that is, light of one color. That means that the source was emitting light of only one color. How does it do that? The way it does that, what that corresponds to, a source emitting light of one color, is this. The source, this is time again, and this is space. And let's say the source is standing here. It's like this. It might have emitted the photon then. It might have emitted it later. It might have emitted it later. It might have emitted it later. The amplitude to emit it at each time is different. So the amplitude to emit the photon at different times from the source is changing. It's going around backwards. Yes, backwards. Like so. Now, to make a quick idea of it, let us suppose, for simplicity, that this function for the photon, just for simplicity, only, but it's right at long distances, only connects 2 points which are going at the speed of light. It's a simple model. It's a simple approximation. So if we were to come over here and get the if I would get the photons to get to here by one route and compare it to another route, when the time is longer, it must have been emitted earlier. If I asked for it to arrive here at a certain time, if it came this way, it was emitted at one time. If it came this way, it was emitted at another time. The amplitude to be emitted earlier. It's going around backwards with time. Yes, so the amplitude to be emitted earlier has a bigger angle. That's why the one that takes longer has the bigger angle. It's not really a property of the photon in the space, like I cheated you in making believe it was. It's really the amplitude of emitting. If you get the photon at a certain time here, it means that it left here earlier. If it went this long route, it left even further earlier. And if this source was emitting with an amplitude which is changing in time, then the amplitude to arrive here by this route and by the long route are different because the source was different. So it's really due to the source that there's a difference in the phase, or the angle, rather, of arrival of the light. In addition, there's one other thing wrong. I talk about light being reflected from a surface, and that's just nonsense. It's not reflected from the surface at all. What it really is it's scattered by the electrons in the material. So the correct picture of this thing is this. I'll draw a better picture. What really happens is that the light comes down and hits the first piece of matter and then is scattered back by that kind of a picture on the last board over there, down here in microscopic view. Or it comes down here and is scattered there, or down here and scattered there. And that's all it does. It's really scattered in the inside, not on the surface. And so we have to add together a whole lot of amplitudes, each of which takes a little longer and have come from the source at a different time. And so it ends up adding a whole lot of little arrows. Each one is a little turned relative to the other by about the same amount. And if you add arrows, each one of which is the same length, and they're turned relative to one another, you go around on a polygon, or if the arrows are very small, a circle. And so you see that the net result, for example, of a certain thickness is to have an arrow, a net arrow, from this end to here. By the way, if this is the center of the circle, that could be represented as the resultant from these two, as this and this together. But that's the way I cheated last time. I just drew these two. But what really was happening was the circle. Let me explain it again. It goes, each little contribution in the interior goes around in a circle. And if I have the thickness just right, exactly right, the circle is complete. And the net result is 0. That's the first minimum. If I go a little thicker, it goes around again and then comes back to 0. If I used half its thickness, it would go around halfway and stop. And in that case, I get the biggest possible amplitude, and so on. So those fluctuations were really not from the surfaces, but from the interior. At least we have the glass where the matter is doing the scattering of the light, and not some imaginary stuff like the surface. I cannot resist. One of my problems is, the problem is with this is that I can make it more interesting by showing you how more and more of the phenomena that you ordinarily see work out this way. And at the same time, I have a desire to tell you about all of the phenomena which are quite unlike what you see, which are quite unexpected and exciting. And I don't know which to do, either to convince you that it's interesting because it's something you didn't understand before, or it's exciting, and the thing to do would have been to give 8 lectures. But I didn't. I only contracted for 4 lectures. So what I've decided to do this time is to tell you about something unbelievable but still true, which is very interesting. So it doesn't explain a phenomenon you know about, but it explains something you don't know about. And that's this. Let's take the simple situation, well, there's many possibilities. I'll say it very neatly. In that we would talk about a photon going from a place to place, and that we could also have it this way or turn it around. We could have the points 5 and 6, 6 being definitely later than 5, 6 being nearly the same time as 5, or 6 being earlier than 5. And when 6 was earlier than 5, it was just a photon going the other way, if you'd like. Now, as it turns out, the same thing. Mathematical form of these functions is very closely related. I think I already told you, if I didn't, I meant to, that d of 2 and 1, if I put 0 in for the mass, that f of 2 and 1, if I put 0 in the mass, is the same as this d. So all the functions are exactly the same, with just one number in them, 0 for the case of the photon. And their properties are very similar. So at first you thought everything was understandable when I drew a picture like that. For example, the electron's coming along, the photon comes, electron goes to another place, and the photon comes out. I did shock you by having the photons come in the wrong order, but it's still all right. But this is a real good one, isn't it? Suppose this point here gets earlier than this point, and I start to draw something like that. Never mind about all the photons, they're in there too, but the point I'm trying to emphasize is the motion of the electron. This is time, and this is space. Question: if this point is called 5 and this point is called 6, and 6 is earlier than 5, I hope to goodness this f is 0, huh? Because I don't want things to go backwards. But it isn't 0. What it says is that this is perfectly possible. And what can it be that's going backwards here? Oh, you say that's easy. It's just an electron going from here to here. Almost. Almost. It's this way, though. The electron carries a charge, and it's good to put an arrow on to remember which way it goes. In this particular case, the arrow is going the wrong way. And it turns out that this section going backwards has many properties exactly the same as an electron, but it's not exactly the same as an electron. It is possible, by getting enough energy, so on, to get an isolated long piece of this backward moving section. See, it goes on for a long way. Maybe it's connected to an electron this way and an electron that way, but it's got a lot of things happening, photons coming in and photons going out and so on, except it's going backwards. You can take a piece of that line and put it between those metal plates that we were talking about, and it curves the wrong way. If you figure out which way the amplitudes are coming and they're changing, it'll turn out that it'll bend the other way. It moves toward electrons. In fact, it's just like an electron, except it's positively charged. It's called a positron, and it really exists. It's easy to make. If you get enough energy with some photons in the fields and stuff, you can produce this kind of a situation. For instance, you can take this and have the following physical possibility. I need more blackboard all the time. Let's see what happens. Yeah, I want that one for later, so I have to have this one. Good. For example, if I drew some terrifying thing like this, with 2 photons, this represents the possibility that an electron and a positron initially in space come together, disappear. No more electrons. Time is this way. Time is this way. Yeah, I know. It looked like I drew the diagram sideways. I didn't draw it. There you got 2 photons out. An electron and a positron can annihilate and emit 2 photons. It's directly observed easily in the laboratory. Or photons can come, I can draw it the other way. Photons can come together and produce that. Produce an electron and a positron pair. So that it turns out, because of this mathematical business, that every particle can go backwards as well as forwards in time if you want. And so for every particle in nature, there's another particle that goes with it matched, which is called its antiparticle, and which has many of the properties of the original particle, with some of them with the sign reversed. In the case of the positron, for example, its mass is exactly equal to that of an electron. It comes from the same function. And its electric charge is opposite in sign. That you can find out by checking some numbers in here. It's all the consequence of these rules. In the same way, there are antiprotons and so forth. And a proton and antiproton can come together and annihilate each other, producing a lot of other particles. For instance, they could produce 2 gamma rays, but it's rare, but it can happen. The other particles I don't want to mention because they come next time. And so we have the possibility of having any kind of combination of these things in space and time, sometimes going forwards and sometimes going backwards. The backwards one's a positron. When a positron is actually made, the way I described there, in the laboratory on the Earth, it doesn't go very far before it disappears because it finds an electron, and the two combine, like the first picture, and 2 photons come out. But you can make them, see them go, deflect them with plates the wrong way, and they annihilate again. They were predicted by Dirac from the theory he had, which was really a calculation of this function for the first time, and discovered very soon afterwards by Anderson in the laboratory. This also permits, well, let me now finish. Well, I don't know if I finish. Yes, not finish. One thing I can't resist. This minus sign is so interesting. It means that when you cross up which is which, you have to subtract the amplitude. And that has an interesting consequence. Suppose the 2 points 1 and 2 are very close together, that you want to emit 2 electrons in the same condition at virtually the same position at the same time. So if 1 and 2 are the same, put 1 here and 1 here, and 1 here and 1 here, because 1 and 2 are the same place and same time. Now you see that this expression differs in no way from this, and therefore the difference between them is 0. That means you can't make 2 electrons, or you can't expect to find 2 electrons any time where they're made at the same point in the same place, same time at the same place. Or if you try to put 3 and 4 at the same point, you see if point 3 and point 4 are the same, these cancel. That would mean that 2 electrons can never be found at the same place at the same time. It turns out what it means is that they try to stay away from each other. Not just because of the exchange of photons, which is one influence which does make them stay away from each other, but by a completely different thing, which is this interference of the amplitudes. Actually, because of the fact that there are polarization cases, it turns out what I said is right, but if you take into account the polarizations also, then you can make 2 electrons at the same point, but they must be in different conditions. One must be polarized one way, and one polarized the other, so that you can still keep track of which was which. So as a matter of fact, you can get 2 electrons into the same condition of, not just, you can put 2 electrons into the same condition of motion, one polarized one way and one polarized the other way, but that's all. You can't put any more. It is on this fact, with its consequences, which is one of the other things I'm unable to show you because of lack of time, the very beautiful fact that all of the chemical properties of substances can be worked out. If we start with a nucleus which has some protons in which are attracting electrons, we start with 1 proton and it puts 1 electron around it. If you start with a nucleus which has 2 protons in it, it's called a helium nucleus, then you can put 1 electron around and put another electron nice and close in the same place. They try to get as close as they can. The other one can be in the same place because of the 2 possible directions of polarization. Now when you take next nucleus, number 3, and you want to put 3 electrons around it, one goes in nice and close, the other one goes in nearly the same place but polarized the other way, and the third one, because there's only 2 ways of polarizing an electron, can't be in the same condition as the other 2 and has to be wander around out here waiting to get in. It's not repelled by any electrical force, it's just repelled by canceling amplitude, by interference. It has to stay out there. It's easy, since it's far away, the photons which it exchanges with the nucleus have small effects. It's easy to remove it. The last electron, in other words, is easy to get off. And that represents an atom which is chemically much more active than helium, because it's easy to remove an electron. It gives an electron up easily. Such a thing is called a metal. In fact, when you compress a whole lot of these atoms together, the electrons are so easily outside ones. They're so easily removed that they just swim around in a kind of sea around the nucleus. They don't even stick on one. They wander off to another one and wander off. They wander all around inside, but two of them on each nucleus is still there. Boom, 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 but one extra ones are wandering around. Such a material, with very little electric forces, you can make all the electrons shift one way or the other. There's electrical conductor. And that metal I'm describing is lithium. It's the first metal. The element before is helium, and it's hard to get its electrons from the inside. Helium is chemically almost inactive, and lithium is chemically quite active and makes a metal, and so on and so on. I am very sorry to have such a brief time to explain phenomena that you know about in terms of these ideas, as the ideas are by themselves are rather difficult to get at, and I wanted to be complete in telling you about the most mysterious aspects rather than cheat by leaving out something important. I guarantee you, aside from the polarization, which is not important, I have now left out nothing, and the whole theory of electricity, electrodynamics, our understanding of the world comes from just these pictures. Each picture is interpreted this way. When you draw a picture, you write an amplitude for this, and this, and multiply it together, wait, and 2c to cut it down. Finally, I would like to describe the motion of an electron in going along. Here's an electron all by itself going from point to point. All right, nothing to that. But it has to be corrected. It's also possible that as the electron was, instead of just going directly from point to point, goes along for a while, decides to emit a photon, and then horrors, it absorbs its own photon. There's something perhaps immoral about it. But it does it. All right, it might not be the nicest thing to do. It does this. And just, you understand what this symbol represents now. If you put some points in here and label these, there's an E for this, an amplitude for that, an amplitude for that, an amplitude for that, all multiplied, for the amplitude for this electron to go from here to here, times the amplitude for the electron to go from here to here, times the amplitude for the electron to go from here to here, times the amplitude to the photon to go from here to here, times C. Those are the couplings for the junctions. And that bunch of junk all multiplied together has to be added for every place that this can be and time, and every place in time that can be. And when that's all done, you've got this piece, which is supposed to be added to that piece. Now when you add this piece to that piece, you find that the motion of this is slightly altered. Its behavior in particular in a magnetic field is changed. In a magnetic field, if the thing was as simple as this, it turns out its polarization changes at a certain rate, or its spin changes, at a rate that can be measured, and which we'll call 1. 1 is the result you would get for this alone. If you add this to this and figure out how the thing moves, it behaves in a magnetic field slightly differently. And if you just add this, you get 00116, or 8, or something like that. If you're this time, for the fun of it, I'm going to write the formula. It turns out that this term is proportional. The contribution in the magnetic field of this is proportional to 2 C's. C squared is 1 over 137.046. Oh, sorry. Well, I did the error. I'm within the error. Over 2 pi. This time it's easy. Our students learn how to do this calculation in their elementary course in quantum electrodynamics, which is the 3rd-year graduate course. All right? This was worked out by Schwinger for the first time in 1948. The next case is to take diagrams corresponding to 2 of these things, something like this. There are other possibilities. Let me erase here and write the other possibilities of this continuing. There are other possibilities, all of which involve 4 C's, C4 somehow. And there are other things that can involve 4 C's. are something like this. Okay, there's a different kind of connection timing. And finally, there's nothing significant about that being straight. These points, it should be, and stuff like that, but I'm too lazy to draw it cockeyed. Here's an interesting possibility. Photon is emitted, makes a pair, electron and positron, and again, if you'll just hold your moral criticism, the electron and the positron annihilate again. So there's an electron going this way and a positron going that way, and they annihilate again into a photon, and that comes back. Huh? It's called a closed loop. It comes and it goes. Huh? This involves 4 C's, 1, 2, 3, 4 also. And this, and this, which involve 4 C's, can all be added together, and you get something proportional to C4, which, by the way, is fairly small, being the square of 1%, which is 100. 1 in 10,000 or so. And the coefficient, this time it's not so easy to write down. It's 0.03 something something. All right. At any rate, this took 2 years to calculate after this was worked out. And it took 1 year to find a mistake in that calculation. It's true. It's true. It was very exciting because it was calculated very carefully by 2 different people. They thought they were independent, but they compared a little bit or something. They both had the answer was wrong, and it disagreed a little bit with experiment. And they improved the experiment, and it disagreed, and it showed that quantum electrodynamics was wrong. No, it was an error in arithmetic. So everything was all right. And now, that was 2 years later. That brings us up to about 1950, 51. And now we go on and we try to do 3. Oh. Well, you see, when you have to add all these possibilities, you get lots of pictures, of which I'll draw one more, but you can keep on going and draw a lot more. You make a pair, they interact by exchanging a photon and so on. And each one of these diagrams represents a definite formula, and we use the diagram to represent the formula. And we just make these pictures, write down what they correspond to, and add the amplitudes. A straightforward cookbook process. All you got to do is write the picture and translate things and write the factors and add everything together. Therefore, it can be done by machinery. Now that we have super-duper computers, we've got so we can compute this one, C6, and by that time it's down to the millionth part. And altogether, so far up to today, as I told you in the very first lecture, this number comes out to be, when you add all this stuff together, don't stop here, but keep on going, 596523 plus or minus 3. Calculated and experimental is 24 plus or minus 2 at the present time. What do we got to do to make it better? Some of this error is that the computer who did this calculation only did it approximately, and we can do it more exactly by using more time on the computer with a little more money. That'll improve the error for that. However, it's no use doing that until we look at number 4. That is C8 with 4 of these extra 8 couplings in it. And people are just beginning to see if they can estimate how big the C8 term will be, because that will be of the same order as this error. In addition, there's an error that comes from the fact that when we go to calculate it, we got to put a number in for C square, and this is as accurately as it's been measured up till now, and a part of this error is due to that. So I have to wait to give this lecture again, perhaps in a year or 2, in which case I'm sure I could write one more figure here, and the error will be smaller. But the question I am not sure of course, is whether it will still agree with experiment. That one never can tell until one makes the calculation more elaborately. I think then that describes the framework of the world as we see it. In the first place, amplitudes for every event that we add together when we expect to add probabilities, and we multiply when we expect to multiply probabilities, but we're not doing it with probabilities, we're doing it with amplitudes. This makes us philosophic difficulties, if you wish, but after a while one gets used to it, one can think about these amplitudes, when you think about adding them, one can consider these as alternatives, which you simply add as amplitudes. And after a while, one gets to be quite familiar with this strange language. The ordinary experiences of nature, such as light going in a straight line, the conservation of energy, and so on, are all very easily deduced from these principles, and all there really is that we can find to all the phenomena that you see every day, with the exception of radioactivity and gravitation, is just the three rules. That a photon has an amplitude to go from one point to another in space given by a special function p. An electron has an amplitude to go from one place to another by another function e. And that there's a junction possible between a photon and two electrons, which has a coefficient which is a certain number. This slightly modified by a couple of cases for polarization, but no more really complicated than that, represents the whole sum of a knowledge, a summary, a most marvelously unified theory of almost all of common experience. But not all. And therein lies the puzzle. There are much more in the world than just electrons and photons. There are the nuclei, protons and neutrons, and so forth. And the theory is therefore not a complete theory of the world, although it is, as far as we know today, a very complete theory of common phenomena. Colors, light, X-rays, positrons, electric currents, electric and magnetic fields, X-rays, radio waves, and so on, substances, hard and soft, chemical interchanges. Some atoms are easy to combine with others, and some are inert. All of this is a consequence, as a result of this analysis, of first finding the right framework, which is the most exciting part of it because it's so utterly strange. But after finding the framework in which to describe things, namely amplitudes, to discover in the end only three amplitudes that you need to discuss. One, a simple junction number, and two, functions, both of which, by the way, are really the same function. In one you put one value of m, and the other put the value 0. So next time I'll discuss the rest of physics and also all the puzzles which are still left in this theory if you thought that was absolutely complete. We still have a question or two to ask about it, and I'd like to describe that and other things in physics for the next lecture on Thursday. Thank you.
Where does coherent light, the light from lasers, fit into your calculations?
The laser has to do with the fact that watch. We spoke about this situation and this situation, only this time I'm going to call it photons. Suppose you have two sources, or two atoms, 1 and 2, which can emit a pair of photons, and you want to know, do you get a photon in two different counters, 3 and 4? There's two ways that can happen. But this time, because it's photons, we're supposed to add these two. Now, if these atoms are in the same condition, or very close, then the amplitudes that we're adding are virtually equal. So the amplitude for the event that the two atoms which are ready to emit produce two photons is twice as big as you would have guessed. If the two photons were different, you would just get this one term because you could distinguish this case from this one. But the two photons are very much the same. You have to add this other amplitude, which is the same thing, except that instead of E's, they're P's. And if 0.1 and 0.2 are close together, or in the same condition, you have to add two numbers which are the same, and therefore double the amplitude, and multiply the rate by 4. So therefore, the rate at which two atoms will emit light, if they emit the same light, is higher than if they emit different and independently. So when there's a large number of atoms, the same thing happens. You have to add all the combinations. And when you have a whole lot of atoms which are all set to emit, that can possibly emit exactly the same kind of photon, they emit much more with a greater enhancement. They all cooperate to emit. They emit with a much higher probability than you would otherwise expect. A laser is a device for producing a large number of atoms in a corresponding physical state, which are all capable of emitting a photon in a particular direction, one kind of photon. It corresponds to all the 3s and 4s being on top of each other. And it has, therefore, when they're all in the right condition to emit, a whole bunch of them discharge the energy into the same photon, and that's what you call the coherent light of a laser. It's a very intense light of a single frequency in a single direction. The reason it works has to do with this interference. It's not very good answer, but it might give you a clue.
Does the amplitude of a photon coming out have any effect on the one going in?
Yes. What we have to do is we have to work out. You remember when I cheated in the beginning, when I was doing this easy, I said all you do is you take the time it took the light to get from here to here. But you see, that really is the sum of 2 times. I could analyze it in 2 steps. I could say there's a certain amount of, there's an amplitude that you come out, amplitude that you reach here, amplitude that you reflected times amplitude that you get here. Now, in multiplying the amplitude to go from here to here by the amplitude to go from there to there, I add those 2 angles. So I add the angle for this time to the angle for that time. It's just the angle for the total time. So that I can analyze this either way. I can either think of it as one photon doing that and consider the total time it went, or I get the same answer if I think of a photon went from here to here, a certain change in amplitude, angle. Then a photon, new one, goes from here to here. That would contribute an angle too. But I say to multiply them in succession. And when you multiply, you add the angles, and that's equivalent to the total time. So it comes to the same answer.
Does the existence of a positron involve some sort of violation of causality?
No. The question was that my description of the positron here involved apparently some sort of interaction, and yet an electron can be all by itself. That was a completely unnecessary difference. There's not an essential difference. I explained the need for the positron by a kind of continuity from this diagram here to this case here, in which the timing is changed, and told you that this function, mathematical function, had to be, this E function, has to be of a certain form where it's completely smooth between here and here. In fact, the mathematical properties are that the behavior when 6 is later than 5 and 6 before 5 are very closely interconnected. One can deduce one from the other. That's all I wanted to say about that. There's no reason why this backwards moving section cannot be a long section, either interacting with photons or not. I gave you an illustration of one where it was a long time going, interacting. But it could be that this positron was made on some star 10 light years away, and it's been going this way in empty space, unperturbed by any photons in the neighborhood, disturbing, you know, it'd be picking them up or not, like it was an electron alone in space for 10 years. Okay? So there's no reason why positrons, in fact, they do. They last, they behave exactly the same as electrons. But for the accident of the fact that the world has so many electrons, the matter in the world has so many electrons in it, so our laboratory walls are full of electrons, and we can't make the positron not hit a wall. If it's left alone, it coasts into the wall. And when it coasts into the wall, it annihilates. So in practice, the positrons don't last very long. But if you get them in a circumstance where there's no matter, we have done so. It's not left alone because of the walls. But you can make them go in a circle by using a magnetic field. And then you can keep them going for days, going around in a circle, untouched by human hands, not touching any electrons, and they stay and they stay and they stay. In fact, we do experiments by making speeding up positrons going around in a circle to a very high energy, and making electrons go in the circle in the opposite direction, and looking at what happens when the electron and the positrons collide with each other. Then we have a diagram that starts out like this. Electron coming in, positron coming in, time is this way. And then things happen. Photon comes, and then one thing might happen is a pair of new particles might come out. If you want to know what kinds of new, could be an electron and positron, it's uninteresting, in coming out in a new direction, you would think that just means a collision. But really what it was an annihilation followed by a recreation. But even more interesting, and I will advertise the next lecture, there are other particles in the world, and this is one way to make them. We can make particles called muons by hitting electrons and positrons together and producing a pair of something else, mu plus and mu minus. So there's nothing different about a positron than an electron. They're all very symmetrical, except history, except the characteristic of our laboratory, that we have a superfluity of electrons. We have an excess of electrons.
Is the direction of time in your laboratory reversible then?
It's a very interesting subject and requires a lot of more serious discussion. Oh, his question was, what about the time in your laboratory? Is it reversed? The order of time, and that is to say the order of events like this, if you put hot and cold things together, then it gets lukewarm. But if you take two lukewarm things and put them together, one doesn't get hot and the other just gets cold all by itself. The explanation of that direction of time, has to do with the confusion of things. If you would take a lot of black things and white and black objects and then just jiggle them, they get mixed up into gray. If you start with gray and just jiggle them, they never get black and white. But each jiggle could be perfectly reversible. For instance, your rule could be just take a pair and flip them over. Take a pair and flip them over. You can't tell whether I'm going forwards or backwards in time. If I take a pair and flip them, that is, reverse them, it looks exactly the same. If I ran the moving picture backwards, I took a pair and reversed it. So therefore, what is interesting is, it turns out that on the microscopic scale, all the laws of physics are exactly reversible. Forwards in time, backwards in time look the same. But all those phenomena, and there are many, of course, life and frying eggs are two examples, which go in one direction only in time, have to be interpreted by the complexity of the circumstances, that there are so many particles getting mixed up, plus some assumptions or understanding about the fact that in the past, the matter in the universe is at a higher density than in the future. This is a property of the universe at large and is not reflected in the microscopic laws. So it does not, it turns out, in spite of the fact that I draw my arrows upside down, end up violating any causal principle. Strangely, it is very interesting.
Whenever you have shown an electron changing direction in your space-time diagram, it has coincided with a junction. Why?
I did that because what I really know, and only thing I do know, is that there's an amplitude to go from 0.5 to 0.6 as a free particle without disturbance. And then there's junctions, and then it goes to another point as a free particle without disturbance. And so I just wanted to represent the functions which I've erased here. By this line, I mean that in the final expression, you will find a factor E56. The line is only meant to indicate that fact. The fact that it's straight is a convention. All right? It doesn't mean that the electron has to go exactly along here or anything like that. All I know is it's generated at 5 and disappears at 6. And it has amplitude E56. Okay? I don't worry about where it actually went.
A disturbance has to travel from 5 to 6 then.
Well, 5 and 6 are the places in which the photon, in this particular case, is coupled. I have only 3 things. It goes from one point to another in a leap, a pure leap without disturbance. The amplitude to do that is that E. Photon goes from one place to another without disturbance. The amplitude to do that is the D. Then there's an amplitude that an electron and a photon and another electron come together at a point. That's C. The 3 rules of nature, or of quantum electrodynamics. If all of nature isn't that would be all there was to it, but that's all there is to the part that we need to do quantum electrodynamics. I guess I'm not used to the kind of politeness you have in New Zealand, because in America, the audience is decreased each time, so let's end up just talking to 4 or 5 people. But I'll try to make it not so painful. We've been talking about or what we're aiming to talk about is the theory that works the best, that we know the physicists like the best, and that deals with a part of nature, and that's quantum electrodynamics, and deals with photons and electrons. Most of the time we've been talking about photons. What we've discussed is that mainly the main idea of the talk is to give you some idea of the kind of framework of ideas which theoretical physics needs in order to describe results of experiments. And I think by this time you'll agree, after 2 lectures, that they're very weird indeed, and quite peculiar and difficult to believe. But I'll just remind you or review for one more time a little bit about what happens with photons. And as we've said many times, 2 times before, we have a source here, and the photomultiplier, which makes counts of photons. Even if we have only 1 photon at a time, and if we have more than one way that a thing can happen. And the example I've been making several times is that the light the photon we could imagine could be reflected from here with a certain probability, and some bounce from here with a certain probability. Let's say 1/5 bounce here, or what do we say, 1/25. And 1/25 here would be 2/25 of them. What we would do would be to add the probabilities. We find out that instead of adding probabilities in such logical circumstances, we add amplitudes. In other words, we can sit around and talk about it this way. You say, well, there's a certain, it can go either this way or it can go that way, and we just add the amplitude before we split. But that means that the logic that we can say that it really goes either this way or that way is false. You can't really say that in the common language way, or you're meant to add the probability. Because if you were to say it can either go this way, some of them come this way, and some of them come that way, you're at a total loss to understand why, when the thickness is just right, none of them come at all. Because if some of them come one way and some of them come in the other way, the fact that they can go both ways surely isn't going to make it that they don't come at all. But that's exactly what does happen. And so the idea to be able to say that it comes either one way or another, it requires that you know what you're talking about. You're not talking about ordinary either one or the other, but either one or the other in the sense of adding amplitude. So it's a crazy game. I still find myself saying, well, it comes either one way or the other. But it is not really true that for a given particle which arrives here, you can say that it either came this way or that way. You won't get the sensible physical idea out of that. As a matter of fact, it's entertaining. The following thing is very interesting. It is possible to put some kind of atoms on the surface here, such that when light bounces off it, they leave some trace, like the atom is left in some other state than it was before. So that if it bounced the light from the surface, an atom on that surface would be left in a different state. Like 2 different surfaces, if there's more than one possible way that something can happen, the whole structure works as this way. In any situation where you have experiments looking at something microscopic, which of course you have in the end to look at something macroscopic that is large, and the photomultiplier amplifies up. When you have a system like that, you can't predict exactly what will happen, but only the chance that the system operates, that you find something happen here. And this probability is always given as the square, or the circle if you wish, of a thing called an amplitude. And this amplitude is a kind of absolute square. It's a special kind of it's the square of the length. And the amplitude is nothing but an arrow drawn on a plane. Now, when something can happen in more than one way, the amplitude that it happens is calculated by adding the amplitude for it happening one way plus the amplitude that it happens the other way. And when you square that, you get the probability. In a problem like this, we have found that the circumstances or the probability for this event might depend upon how far apart you put the plates And you get reflection from a pair of plates which varies with the thickness in that manner. And so, this, in our particular example, I finally found out that that was 16% and that was 8%. From each surface, there was 4%. Now, if this were a more ordinary thing, like you would expect, an ordinary type of reasoning instead of this esoteric subject of microscopic physics, you would expect that the chance to arrive here could be analyzed by saying, of all of the ones that come down, some bound. The problem is, what is the chance, if we have a source here and these layers here, that the photomultiplier goes off and one of these atoms on this layer here, say, is excited? That's a different problem, has a different amplitude. And that has nothing to do with what happens down here. And that amplitude is 4%, or 0.2 rather. Squared is 4%. It has some darn angle, I don't understand angle. Squared is 4%, and the probability that it's reflected from the front surface as detected by an atom there is 4%. Likewise, if you ask for the following situation, that the photomultiplier should go off and the bottom one should have an atom excited, you get also 4%. So you see, if we try to test whether or not it's going one way or the other, then the results of the experiment are changed, or another way, we have to ask about a different experiment. The case of interference is this, that it is such a situation that the rest of the system, the glass, is exactly the same before and after, and there's no way to tell where the light bounds. Otherwise, if you had some way to tell, you'd ask for a different physical result, have a different amplitude and different results. Which means these things I point out because as you've gone along, you've probably struggled to find some kind of a simple-minded explanation of these things. But when you see how annoyingly complicated it gets, I mean not complicated, but curious it gets harder and harder to make a simple model. So we've given up on that. I also emphasized last time that you can get some that one of the things I wanted to emphasize is that things that are very common and observed all the time and which are perfectly obvious are quite different in this world. It turns out that what we thought was obvious is why we can put atoms of this kind. It's rather technically difficult with light, but you can do it in many, many analogous experiments in similar situations. Well, imagine we can do that with this. And then we could say, let us bounce the light, and then afterwards look at the atoms and see which ones are excited. What you discover is, if you have enough here, that you don't miss them. If you forget the cases where you miss, that it's either excited here or it is excited there, yes. In other words, it does look like the photon either goes this way or that way. And when you have the atoms here and you count just those cases in which you can find, you see, I'm worried about the cases where you miss them. Forget the cases that you miss them. And take only the cases where either one or the other atom is excited on one or the other sheet, and ask for the probability of arriving here. And you know what you get as a result of the function of thickness? A completely different result. If you have atoms there that can leave a trail as to whether light was there or not, you get 8% reflection no matter what thickness. In other words, it tricks you. You're only going to be clever. You know that if you have no way to tell from which one it comes, if the light after it bounces off leaves everything the way it was before, then you get this funny interference effect. If, however, you put something here to see if the light bounced here or here, you can tell it bounced one or the other. It tells you, it leaves the atoms excited. But lo, there's no more interference effect. Why? How do we describe that? It's not hard. It's that we changed the problem. The first problem was, given a source here and material here, what is the probability that for the following event, that the photomultiplier goes off and that the system is left exactly as it was before, that nothing is changed in the glass? That's that curve, the first one. But in the second experiment, we're asking for a different final problem. We're asking a different